Okay. And then I'm going to share screen. And we're going to go here. And I'm going to go to presentation mode. And you guys should see this. Okay. Well, thanks everyone for coming today. Appreciate it. Sorry about the rigmarole here with the makeup and everything, but I'm glad you can sign in there. Great. It's here. Okay. So just kind of a quick recap. Oh, come on, buddy. Here we go. Click in here. Any questions from last time? We spoke about the advantages of lightweighting and how different car companies think of different weighting. We looked at some examples of some, I guess, some structures that are nicely optimized. And we talked about how the transition in racing bicycles switched from steel to carbon fiber and what that's really meant. Kind of huge decreases in weight. So today we're going to jump right in. Okay. And in case I did say this the last lecture. The most important thing I think I want you to walk away from this class is just that you have to be concerned with geometry and materials. You never get to the lightest weight solution unless both of those have been addressed. There are a lot of mechanical engineers who, from my experience, are real interested in material science, and they tend to not think in terms of how can I make a material that does better. And there's a lot of material scientists I've known who sort of aren't that interested in mechanical engineering, and they don't think in terms of, how do I shape structures? How big does it have to be? What's the diameter? There's going to be a lot of material scientists who look in that direction. But the problem is that those two groups maybe don't speak to each other real well, and really have to get both of them in place in order to really get to the latest solution. Okay, so I like to teach with some case studies sometimes. So we have two useless sports cars. You can't get much more than a grocery bag in them. And they're really, when it really comes down to it, they're really just basically people who want to do track day weekends. They're not much useful for much besides that. Although they don't get bad gas mileage either. So if you're willing to sort of stuff yourself into one, then drive long distances, you probably save a lot of gas. Thank you, appreciate it. You can probably save a lot of money on gas, because some of these things get pretty good gas mileage. Although a lot of times the Aero is pretty horrible, so they don't do so good on the freeway. So here you've got these two cars. Say it's your left is the Lotus Elise, and on your right is the Renault Spider Sport. Okay, both these cars came out kind of mid-90s, right about the same time. And they're both, if you look at the wheelbase and you look at the tracks, the distance between the center lines of the wheels, you look at those, and they're you take maybe that product of those two, they're about the same size. They're really close. One of them the Lotus has a 1.8 liter engine, and the Renault has a 2 liter engine. This was at a time where it was very fashionable to try to make body structures out of extrusions, aluminum extrusions. So both of them were made out of extrusions, and both of them had bodywork made out of fiberglass. So both were basically some type of layup. They weren't like RTM, resin transfer molding. They were just some type of basically hand layup. But the difference, the interesting point is that even though these cars are so similar, there was like a 450-pound weight difference, which is huge, right? When you consider that's almost 30% the weight of the car. It's a huge difference. So what gives? Why are they different? Why do they have such different weights when they're basically the same car? The difference came down to how the tubes or the structural members, the aluminum structural members, were joined together. One of them used structural adhesive, and one of them used bonding. One of them used structural adhesive, and one of them used welding. So I'm showing you this example to show that there really is a difference, that you really can, as an engineer, you really can influence the weight of something. There are certainly knobs that you can turn, and there's knowledge that you have that gets you to a better solution. It's real. So here's what happened. Both these cars are made out of, I think they were a 6000 series aluminum, precipitation hardening aluminum. And that's what they use for the extrusions. And I think it's a 6000 series. So the one that was welded, when you weld a precipitation hardened aluminum, you dramatically change the microstructure around where the weld is, where it got hot. So these materials, I'll talk about this later, but they strengthen by precipitation hardening. When you heat these materials up, you destroy the precipitates, or you grow them to the point where they're not going to do their job very effectively. We'll talk about this in a second. But so the material is severely weakened in what we call the heat affected zone. And because of that, in order to make sure that these body structures were strong enough to support the weight of those vehicles over long time periods, fatigue resistance and all that, they had to make the you have to make the material thicker in the heat affected zone. But because these are extrusions and these are not real expensive, in the grand scheme of things, these are not real expensive cars. You have to carry that same thickness through the whole part, the whole wall thickness of the whole extrusion, right? So that means that you have lots of extra material there that's not doing anything. I mean, it's not doing anything, just weighing the car down. The Lotus, on the other hand, they knew about this effect, and so they used special structural adhesives at the time. They were developed by a company called Ciba Geigy. And these were very innovative at the time. This was pretty new stuff for cars. I guess they've been using for a while in airplanes. But this was new stuff for cars. And because they were able to bond all the parts of these extrusions together, they didn't have to use thicker material. They didn't have to worry about a heat affected zone because the material was the same, call it virgin strength that it was when it left the extrusion plant. So they were able to use thinner tubes, thinner structural members everywhere throughout the whole vehicle. And the result was that the car was 450 pounds lighter. So this is interesting. They on bicycles, on racing bicycles, or not, touring bicycles too, where there's they used to use a lot of steel, back in the 80s or 90s. Prior to that, what they would do is they would make the tubes would be thinner. The wall section would be thinner in the middle than at the ends. They would have what's called a butted tube, so it was much thicker at the ends. And when they brazed or welded the tubes together, they compensated for the drop in strength in the heat affected zone by making that area thicker. But because bicycles are small and people will spend lots of money for bicycles, they can afford to make these what they call butted tubes. So they're thicker on the ends. The wall thickness is thicker on the ends than it is in the center. So that's how you reduce weight in a bicycle. And this is a similar kind of strategy that Lotus used here, except they avoided the problem altogether. Okay, so remember this one, welding. I know Professor Eager is a welding expert, but I think that maybe that accentuates the point, is that you have to have an expert when it comes to welding, because there's so many ways to screw it up and lose fatigue strength or lose strength altogether. So just if you can, sometimes I've told a lot of people I've worked with over the years to avoid welding if you can. If you can glue things together, great. Of course, you can't always use structural adhesive if it's high temperature, because it'll basically turn to carbon and burn off. So, but just keep that in the back of your head, that a lot of times you can make a better structure by structural adhesive rather than welding. And watch out for silicone. Don't ever get silicone on there because the adhesive won't stick. And there are silicones in surprising places you may not have thought of, like lubricants for skill saws. Okay, so let's talk about designing materials. How do you design a material to maximize the potential of reducing the weight of a vehicle or any structure? And two quotients that come to mind are the strength divided by density and the stiffness, or the Young's modulus divided by density. We call these specific properties. So specific strength, specific stiffness. When these values, or these quotients, are high, that means there's more chance to use less material and still have the structure have the same strength. So we're after light weighting. Okay, so the ideal world is that you can attack both of these. You can increase the strength, you can increase the Young's modulus or stiffness, and decrease the density at the same time through alloying. Right? That rarely happens, but you can do both. Rarely happens. There's a good example of aluminum lithium, which I'll show you in a future lecture. But typically, you're stuck just changing the strength of the stiffness. Usually the density won't change much. Okay. So these are two quotients. There's other ones. Okay. There's impact absorption energy. How much weight does it take to absorb a certain amount of impact energy? There's fracture toughness. There's creep resistance. If it's hot, it's hot. Fatigue resistance. Fatigue, all those scaled typically with tensile strength. So anyway, just keep in mind we're gonna focus on these two quotients here. Okay, because there's enough material here in detail here. We can study this for the next 10 years, but so we're just going to stick with those two for now. But keep in mind that there are some others that are important as well. So how do you increase the strength of the material? How do you increase the stiffness? Well, we're gonna focus on strength today. We'll talk about stiffness in a future lecture. But there is a whole science. A lot of it started here at MIT. Some of it started at Northwestern University in Chicago, around how do you design materials for higher strength. The perhaps one of the most important first concepts that has shaped materials design for decades was from Cyril Smith here, who was a professor at MIT. And I think he was the first guy to really look at materials as systems. You know, you might think of like, okay, the brake system on your car, the propulsion system on your airplane, you know, the power generation system in your power plant. Those are systems, right? And it really, no one had really thought of a material as a system until I think this guy, Cyril Smith, started philosophizing on the idea. And he wrote a bunch of papers on this concept of you know, materials as systems and subsystems and hierarchies of systems and subsystems. One example is this steel grain right here. So there's the grain, that's a system. There are packets in there of different microstructures. Those packets contain martensite lath. Within the martensite lath, there are different blocks. You know, if you've ever looked at martensite, it's little needles and things that come together. So this is a hierarchy of systems. The grain is the biggest system. And as you start looking smaller and smaller and smaller, you know, you start seeing other systems. And this can be a lot of fun. I mean, how many guys are ME majors and how many are Mat Sci guys? One Mat Sci, two Mat Sci? Okay. So we got 3 MEs and 2 Mat Scis? Okay. You know, this can be a lot of fun. I don't know what the access here is to microscopes and things like that for anyone who wants to go look as a student here. But just to take a piece of aluminum or a piece of martensitic steel, mount it, polish it, look at it in a microscope, etch it, look at it in a microscope, just gotta etch it. And then you can start zooming in at different places. You see completely different things at different length scales. And this is this hierarchy of systems. So just like any power plant or car engine or braking system, you can optimize the subsystems to make the greater system work better, right? If you're building a brake system for a car and you want to make sure that it can stop a lot without the brakes eating it too much, you need a bigger rotor. Okay, you need a bigger rotor. Well, how do you take advantage of that bigger rotor? Then you go to the brake caliper subsystem and you start looking at the pads and so forth. The point is just that as an engineer, someone designing a material or designing any system, you can look at the subsystems, optimize those for the good of the overall system. But you have to be careful because sometimes you can over-optimize something at a subsystem level, and then that can actually be detrimental to the overall system. So always think about what is the overall system and how's that gonna behave. The fundamental paradigm of material science, as some of you guys know, is the processing, structure, property, performance relationships. Right? This paradigm has got me out of all kinds of messes in the past. I've used it a gazillion times, and it's always steered me in the right direction. You can think of these as systems. You know, there's 4 systems here. The processing is a system, the structure is a system, the properties are a system, the performance is a system. The concept was largely discussed by Morris Cohen, who was also a professor here in the material science department long ago. Back in the 50s, when people were doing a lot of metallurgy and that was a really popular topic and things, there was a lot of science going on. I think Professor Eager talks a lot about science versus engineering. There's a lot of science going on back then. People looked at a material and they said, okay, well, what if we put in these elements? You know, what does it look like under the microscope? And then, well, if we stick a hardness indenter into it, how hard is it when it's got this microstructure? You know, let's try heating it up and cooling it down really quickly. What happens then? What does that do to the microstructure? Here's what happens. So scientists move from your left to the right. Okay, they go this way on this paradigm. Right. So this is what Professor Eager talks about. He says, what is it? He says, scientists, help me out here, Tom. Scientists try to figure out why things happen, and engineers try to make people's lives better. I think that's his definition. So this went on for decades, and there was lots of great papers published on correlating processing to structure, and then to some property, hardness or fracture toughness or creep resistance, right? And then at some point, engineers like Greg Olson at Northwestern, materials engineers, took over and said, well, what if we want to design materials? What if looking at a book is not good enough? What if looking at the strength of 6061 aluminum isn't good enough? What if we could do better? What if we could incorporate what Cyril Smith was talking about and these properties, structure, process, structure, property, performance relation? What if we could put all this together and actually design materials, make them stronger? Mr. Mechanical Engineer, you know, how strong do you need your part? You know, let's work backwards. Let's say if you need some performance, the strength of the part can take 5,000 pounds of load and it's only this big. And you know what you can very readily calculate with finite element analysis or with just hand calculations, what's the property? How strong does it need to be in order to support those 5,000 pounds? And then, well, what structure is going to get us those properties? And then how do we process this material to get those structures, to give us those properties, to get us the performance we want out of the part? So engineers go from right to left on this chart here, on this paradigm. The state of designing materials has I think increased or has advanced rapidly, say in the past 20 years or something, 20, 30 years. There's many groups around the world that work on computational models to try to calculate out those different links. You know, if you put 10% aluminum in and you put 5% magnesium in and you put 20% chrome in, what is this thing going to do? So there's, you know, what structures are going to form if we stick all those together. So there's groups that have developed computational models that allow you to predict those things. The success of this has been pretty remarkable, and this led to President Obama's Materials Genome Initiative. And this is a realization. These people realized, the government realized, the U.S. government realized that, hey, you know, we can get to material solutions. We can get new materials to market much quicker if we use these computational models rather than doing things by trial and error, by mixing things. Okay, what happens if we mix this and this in a laboratory or a foundry? This takes too long. It's too expensive. So the government decided they wanted to support this effort, and they put a lot of money into developing databases and supporting groups that were working on modeling, computer modeling, and they bought these groups expensive computers and went on and developed these tools. So the Materials Genome Initiative has been a big prize, a big reward, I think, for the material science community to develop these models and improve methods of computational materials engineering or integrated computational materials engineering. And it's pretty exciting. This kind of all started back in the 50s and 70s, let's say, here at MIT, actually. Professor Eager has told me that there was a professor from Germany named Wagner, I think, Wagner. And he came to MIT from Germany and then worked with Cohen and Kaufman. So Morris Cohen and Kaufman was his grad student. And they wrote up what's called, they started working on computer models that would predict phase diagrams. So you guys remember what phase diagrams are? You know, it's basically a map, right? It's a map of temperature versus composition. You got this composition, you got this temperature. You end up in this field here. That means you've got phase A, you've got martensite, you've got austenite, whatever it is. That's a phase diagram. They were curious, you know, how can we calculate these phase diagrams based on what's called Gibbs free energy? And they wrote a lot of papers, and they started what's called the CalFAD movement. So calculation of phase diagrams is CalFAD, but I think that was the original definition. Now CalFAD is used for many other things. It's also used to define not just the processing structure link, but also the structure property link. So the landmark paper, from what most people consider, I think, the start of computational materials engineering, is this paper that's shown here from Kaufman and Cohen. And I encourage you guys to go to the library and buy and download this paper. I've done it. It's fun to read. It's a very interesting paper. And I guess somehow I got to get you guys a copy of these slides, so you can probably look it up. But it's Kaufman and Cohen, and it was a really interesting paper. The the CalFab movement moved on, made progress. There was a program that was developed called Thermocalc. Thermocalc uses these thermochemical databases to calculate out phase diagrams. So it's sort of the next, it's sort of the commercialization of CalFab, let's say. You can buy Thermocalc software. There's the students, I'm sure you guys can get licenses on campus here. I guess you have it too, or if you used it, have you used Thermocalc? Okay. So this Thermocalc is it's really interesting. You can calculate phase diagrams using composition and temperature and a bunch of other things. We'll talk about it some more. The Steel Research Group at Northwestern University ran with this, and they've done a lot of research, led by Greg Olson, who's now also a professor at MIT. They've done a lot of this, and they've developed incredible materials. Started a company called Questech that does design of materials, steel and aluminum, and titanium and nickel. And they, at the beginning of their work, they focused on developing bearings. There was a project that they worked on that were some really high strength, high fracture toughness stainless steel bearings that went on the space shuttle. You know, actually they used them. I think NASA used them. And then later they started focusing more on landing gear. How do we develop materials that are really strong, you know, really strong at the same density or close to the same density, so that we can reduce the wall thickness on a landing gear strut or something. Okay, and they developed this cerium alloy, and I think that actually went into production on some aircraft. I'm sure Greg Olson can tell you more about it. The government caught on at some point in here, like I said, and then came the Materials Genome Initiative. And now the NSF and the National Science Foundation, the national academies, they're all very interested in the Materials Genome Initiative, and they're all very interested in supporting it and paying grad students and so forth to develop models and databases. So it's all sort of a really beautiful synergistic effect, and computational materials engineering is really, I think, growing very rapidly. And there's been a lot of really, really admirable advances. So I'm really excited about that. You guys can read about it too. And I should point out that I lifted the slide from Kuman and Greg Olson. I didn't make this slide, but it's such a nice slide I wanted to show to you. Kuman is one of Greg Olson's grad students. He's now head of materials for SpaceX and Tesla. So you guys watched the Inspiration 4 launch last week? Anyone see that? You guys know about it? This is the first time they took 4 civilians, not just put them in space, but put them in orbit, and they went around 15 times. And this is the first time that happened. But the reason I bring it up is that there are some stainless steels that are very, very have very great properties, very high strength, very high fatigue resistance, very high corrosion resistance, that have been developed at SpaceX by Charlie Kuman and his group that have gone on real spaceships, like I think the Atlas. What's his big stainless steel rocket? It's called the Atlas. Anyway, Starship. Thank you, Starship. So Elon Musk Starship. That's stainless steel that was developed at Tesla. I mean, at SpaceX. Same thing. And then that is the same material they were planning on using on the pickup truck. I'm not sure if they're still going to do that, but okay. So back to this. Cohen's reciprocity. The point is, you can go back and forth. Scientists go from the left to the right, your left to the right, and engineers go from the right to the left. So here's sort of an expanded view of that fundamental paradigm of material science. I call this an Olson diagram because Greg Olson, I think, invented it. And this takes the primary or the fundamental paradigm of material science, and it combines it with the stuff with the concepts that Cyril Smith developed about systems and subsystems and hierarchy of materials and systems within the materials. And this Olson diagram shows how helps provide a framework so you can develop these concepts of processing, giving certain structures, giving certain properties. Okay, you have on the far left here the processing structure, the processing systems or subsystems. These can be things like mixing alloys, deoxidizing, desulfurizing, solution treating, quenching, tempering, precipitation hardening. In the middle are structures. These could be grains, they could be martensite lat structures, they could be sulfur stringers, they could be precipitates. These are the microstructural features that help to define a material. I've just mentioned a bunch of metals, but you can do the same thing for polymers. You can do the same thing for ceramics. You know, those materials have their own microstructures too. On this side, on the right here, these are the properties. So properties can be all kinds of things. They can be fracture toughness, they can be hydrogen resistance, they can be stiffness, they can be density. Those are properties of materials. And then these things, of course, come together to give you a performance. And my experience is that oftentimes getting from here to here is much more in the mechanical engineering realm. Things like finite element analysis, that could be strength finite element analysis, that could be thermal finite element analysis. Combining CAD geometry with finite element analysis gets you from properties to performance. Okay, in our case, for light weighting, we're mainly interested, like I mentioned before, in this strength to density, specific strength, Young's modulus to stiffness, or Young's modulus to density, or stiffness to density. And then there could be other properties. We're not going to worry about this one for this class. We're just going to focus on those two. But those two together give you light weighting. Now we have to work backwards to figure out what microstructures get us these, and then what processing is going to get us those microstructures, is going to get us these properties. And that's what we're going to talk about. So here we are back to this. For the next couple minutes here, we're going to focus on strength to density. Okay, now density, like I said, you can't really, for the most part, you're not going to change that much. Going from a stainless steel to a high strength, low alloy steel to a low carbon steel. Yeah, stainless steel is a little bit denser, but for the most part, this isn't changing by much. You guys seen these before, the Ashby diagrams? Yeah, these are really fun. These are really fun. These are maps of property versus property maps. And then the bubbles sort of show where these different materials would lie. So here, this is one I have here of strength to density, okay? And these bubbles represent different material systems like aluminum, steel, what we got here? We got copper, tungsten, titanium, wood, stone, cork, everything's up here. Everything's up here. And this is usually a good place to start when selecting a material. Strength to density, you want to find something that's as far to the upper right here. That's your right, okay, upper right here. Right, those are the materials you might want to focus on first if you need to maximize strength to density. So, sorry, I messed that up. I'm sorry. You want to go that way. So you want to be low density and high strength. It's going to be that direction. So you might look for, if you're trying to lightweight structure, you want to look for materials that are on that side, the upper left corner. Understand? Okay. We'll get back to talk about these some more. Goal setting. So I remember I first took Greg Olson's materials design course a long time ago. And I kept, he kept saying, well, we're going to make a material that's this strong and this stiff and blah, blah, blah. And I kept thinking, how can this guy like say that? How does he, I can pick all kinds of crazy things out of the air. I want a piece of wood that has a yield strength of 15 gigapascals. It's not going to happen. It's never going to happen, right? But what Greg Olson was saying with this is just that if you know the properties of one material that you love, that maybe has a high strength, maybe there's another material that has a high fracture toughness, and you understand the different microstructures that are from which these materials benefit. What microstructures are giving the high toughness? What microstructures are given the high strength? How does that happen? And by the way, Rockwell C, this is a good proxy for strength, for tensile strength, just so you know. So by understanding, like, okay, if this one has this microstructure and that's making it tough, and this one's got this other microstructure over here and that's making it strong, can I combine those together? Can I combine those together to make a material that has the best of both of those worlds? And then you can start thinking in terms of, here's a reasonable box. I know that I could probably get close to being in this box. There's a good goal right there. Knowing that I'm going to try to incorporate both these microstructures, I have some idea how to get those microstructures. I have some idea what the processing is that's going to give me those microstructures. I can begin to get pretty close. Let's take a goal like that right there. And that's how goal setting is done when you're designing a material. Knowing what microstructural properties, what microstructures give the properties, can you combine those two together to give you the strength or toughness that you want. You need to think in terms of what's happening at different length scales. How do you combine those different microstructures together? Here's the kind of gamut, I think, for a metal of the different length scales and microstructures that exist at those length scales. There's the atomic level, right? There's atoms. There's missing atoms. There's interstitial atoms that sit somewhere in the lattice. There's substitutional atoms that, you know, if it's a matrix of one material, maybe there's another part that sits in a lattice location. There are dislocations. So dislocations are kind of an abstract concept, but basically they're just a missing column of atoms in a lattice, which leads to it's called dislocation in a Burgers vector. Anyone taken a class in dislocation theory? Sort of? Okay, it's hard to understand. There's lath, for example, martensite, these tiny little needles that interlock and make the material strong. There's precipitates, like 6061 aluminum. It's a precipitation hardening aluminum. And these are, you know, the length scale that's shown there. There's inclusions. I always say to people that sulfur sunk the Titanic, right? The material, when they made the Titanic, the material specs weren't that clean back then. And the steel sometimes had a lot of sulfur in it. Sulfur combines with manganese to form manganese sulfide stringers. These can be highly detrimental to the toughness of the material. So I've actually seen micrographs. I have a book at home. Micrographs of the steel from the Titanic, and it was full of sulfur stringers. And when the ship hit that iceberg, bang! Everything just cracked open because it was cold. It was below the ductile brittle transition temperature. You know, which the reason it was so brittle at that temperature is because they had all these sulfur stringers in the microstructure. It hit that iceberg, and all that steel just snapped apart. And then the water came in, the thing sank, and we've got, you know, Leonardo DiCaprio and Kate Winslet, you know, clinging to a piece of wood in the middle of the Atlantic. So you guys this is, you know, as materials engineers, this is your responsibility to always push the boundaries on how clean a steel you're willing to accept. Sulfur stringers can be so dangerous, and I can tell you that certainly in my career I've come across steel that I've rejected, saying, hey, no, there's no way we're going to use this stuff because it's going to be too brittle. So always ask that question: what's your sulfur concentration? Try to keep it below like 0.04, 0.03. I think is a 0.03 weight percent is in my mind, is kind of a maximum for the amount of sulfur. Try to keep the manganese to sulfur ratio over 15. That's always what I try to do. It's always worked for me. For the length scales, then for anyone who's ever looked at a micrograph of a piece of aluminum or steel or magnesium or titanium, they're made up of these grain structures, right? That's a little bigger length scale. Then finally, you think in terms of grain boundaries, but grain boundaries kind of span a large spectrum of different length scales because, you know, they're one hand in one direction, they're you know, angstrom scale, in the other direction they can be millimeters. You guys ever seen like galvanized steel with the huge zinc grains on the surface, right? You've seen those? Those are big grain boundaries, they're big grains, and they can sometimes be centimeters. Dislocation theory. So dislocations, like I said before, are a missing column of atoms. If you did a calculation about how strong is a crystal of material, of steel, or, well, that's a bad example, aluminum, iron, titanium, you know, pure materials, like what should the strength of that crystal be based on the amount of energy it takes to pull the atoms apart from one another? Okay, you get one big number. Those things are really damn strong. But when you actually test real materials, of course, they're not that strong. They're down here somewhere. Why is that? And this is something the scientists, you know, material scientists figured out. They found that materials deformed by these dislocations. Instead of ripping the atoms apart when you deform a material, these dislocations move through the lattice. And the energy that's required to move those dislocations through the lattice is much smaller than it is to rip apart all the atoms. So that's why materials aren't as strong as the theoretical calculations would predict, because it's, like I said, it's much easier, much lower energy to move dislocation. But if you start thinking in terms of how do I engineer a material? How do I design a material so that it's higher strength? What might you do? You might ask yourself, how do I stop these dislocations from moving? Right? Maybe I don't want to completely stop them because I don't want them to split at the atoms because it might be brittle if it does that. But how do I slow these things down? How do I increase the energy? As a materials engineer, as a materials designer, how do I increase the amount of energy it's going to take to move these dislocations through the lattice? It's a key concept. Remember this one, okay? And then you start thinking of this in 3 dimensions, atomic planes and missing little triangles of material. Some of the mechanisms that you can use as a materials designer to increase the amount of energy it's taken to move these dislocations through the material there's a lot of good ones. I'll describe a couple of them for you here. One of them is work hardening. So if you've ever taken a paper clip and then bent it and bent it and bent it, before you broke it, you'll notice it gets a little bit harder to push each time to actually get it to plastically deform. Right? That's what's happening is that you're taking these dislocations and as you deform the paper clip, these dislocations are moving along the lattice. Eventually they kind of tangle up in each other. Right? And then it becomes harder to move them, it takes more energy to move them, so that's an increase in strength. This number amazed me. This number never ceases to amaze me that there are, like, in a tiny little, like, centimeter by centimeter by centimeter piece of aluminum, there can be kilometers of dislocation length. All this tiny little atoms and missing things, like the actual length can be kilometers inside a little tiny cube. That's how many dislocations there are in some work hardened pieces of material. The strength from work hardening can be calculated. Do you have a question? Okay. The strength of the material can be estimated using this equation here, which basically says that the strength is going to go with the dislocation density to the half power. So more dislocations, more strength. And dislocations, you don't just move them when you start straining a material, when you start plastically deforming material, you actually generate more. So you're generating all these more, you got dislocations going to one another, that increases the strength. So work harder, that's a way to increase the strength of a piece of aluminum, a piece of steel, a piece of titanium. Another mechanism is substitution strengthening. This is alloying, right? This is making a solid solution. You have some lattice of material, and then you have some alloys, some solute materials, the smaller of the two. And you alloy a material with this, and then those solute atoms go somewhere. Sometimes they go into the lattice positions. They kick out one of the solvent materials, okay, and sometimes they end up in between them, the interstitials. So they call those interstitial solution strengthening. And by having these solute atoms that either occupy a lattice location or end up between the atoms, you make it harder for dislocations to move through the lattice. So that's strengthening again. Okay, so it turns out actually that the interstitial solution strengthening works better. That can get you higher increases in strength. But if you have a bunch of iron and you have a bunch of sodium or carbon or boron or chrome or whatever you have, how do you know which one's going to end up at the interstitials and which one's going to end up being a substitution? And the way you do that is the rule of thumb is plus or minus 15% the atomic radius. So if the material has plus or minus 15% the atomic radius of the solvent material, in theory, it probably happens most of the time, those atoms should occupy a lattice position. Smaller than that, and they're more likely to become an interstitial. And that's what you want, actually. That's what you want. You want this increase. This will give you a bigger increase in strength. Some examples of a substitutional. So solid strengthened material is like brass. Okay, some examples of an interstitial strengthened material is steel. You have little carbon atoms that occupy locations in the interstitials between the iron atoms. Okay, and steel is a lot stronger than brass. Question?
So would this be with like a dopant amount, like a very small percentage, or is it more like actually alloying?
This is typically a small percentage.
Okay.
This is typically a small percentage. I mean,
Would that be like when you're just like casting a belly, you can just like insert a small percentage of
right,
okay.
right, or making an ingot, right? It may not just be casting. You might be casting out an ingot, or what's the difference there? I guess when I think of an ingot, I think of something that's rolled. When I think of casting, I think of just a molding or molten metal in there. But the amount of carbon it takes to increase the strength of steel is so tiny. It's so tiny, and the differences are so huge for such a tiny amount. You talk about a 1008, a 10008 steel, AISI 10, that's point. What is that? It's 0.8 weight percent of carbon, right? Did I do that right? I did that wrong. 0.08%, 1008. If you talk about a 1080 steel, that's 0.8 weight percent of carbon. So it's less than 1%. It takes a tiny little bit. You rarely see, when you start talking about steels that have like full percentages, then they become iron. They become like cast iron, like ductile cast iron or gray cast iron. those type of materials. Those have over a percentage of carbon.
Um,
Okay, so that's part of what Bessemer figured out, right? You take the carbon out of steel and it becomes more ductile and stronger. The reason for that, by the way, is if you have too much carbon in there, it begins to form carbides with the steel, and those are brittle. They can make the material not as strong. Apparently the valence of a material, the number of electrons per atom, can have a very marked increase in strengthening capability from substitution strength. Here's a graph I stole out of Dieter that shows how as you go to more electrons per atom, you actually increase the strength if you can put them into the solid solution, copper for this case. It's one of my favorites, precipitation hardening, right? So you take a piece of aluminum, like a 6061 aluminum, like a 7000 series aluminum, like a 2000 series aluminum, and take, for example, like 2000 series aluminum. So 2000 series aluminum has a lot of copper in it. That's the main alloy element. 6000 series, I think, is silicon and magnesium and aluminum. And you take these materials, you heat them up to some temperature that's shown here, 500 degrees Celsius, and all those atoms diffuse and they're moving around in there with all the other atoms. And then if you take that material and quench it, they kind of get locked in position. And with time, what will happen is those atoms will diffuse together and make little precipitates. They start off really small, like a nanometer size. And then with time or temperature, they'll grow a little bit. And then there's some optimum size that gives you the highest strength. That's here. This is aging time versus strength. So legend has it that there's some scientists way back when, I don't remember who it was, probably Professor E, you can tell me, who material scientist, and he made some aluminum. I think it was a he. He made some aluminum, and he was really happy that he had produced something that was so strong. He came back a week later, and it was a lot weaker, and he didn't know why. So what happened is the material artificially aged, and these precipitates got too big, and then they didn't strengthen the materials efficiently, right? So with aluminum, for example, another thing you need to know about this is that the actual strengthening can take weeks. If you're running an aluminum factory or foundry, you don't have weeks to wait for your billets or your wrought material to get stronger. So they do what's called an artificial aging step. So they take a piece of aluminum and they stick it in a furnace. They heat it up a little bit, not too high, maybe just like 300 degrees Celsius. Let it sit there for a couple hours and grow the precipitates to a certain size. Then they take the material out and precipitates stop growing at any kind of appreciable rate. Those are the precipitation hardened aluminums. So this is getting over this hump can cause a lot of problems, and a lot of mechanical engineers that I know fall into this. A lot of factories fall into this problem. I was once responsible for a casting that was going to be used with a motor. So we had an electric motor, and we had this aluminum casting, right? Okay, and we had to drop. Well, actually, it wasn't a casting yet. It was going to be a casting. It was a machine 6000 series aluminum part is what it was. So we got this housing that's made out of aluminum. We have this electric motor that we're going to drop in there. It's made basically out of silicon, high silicon steels, laminates, and the armature and everything, and the magnets. We're going to drop this thing in there. So the problem is that how do you stop the motor from rotating relative to the housing on the aluminum? You have to have some way of doing that, but you can't like put a bunch of bolts in there because it take too much time to bolt it down, or it might cause distortions. You have to increase the size of the gap between the rotor and the stator. You don't want to do that. So how do you get these two together? The way that a lot of companies do this is they have an interference fit. So the aluminum is a little bit inside the aluminum parts, maybe a little bit smaller than it should be, maybe by a couple tenths of a thousandth of an inch. And the motor's maybe a little bit bigger. And the way they do this is they freeze the motor, or they heat up the aluminum. Okay, whichever works easiest for them to do one. So I was responsible for this part, and we're running this motor one day. We're testing it. It blew up. It exploded. Aluminum shrapnel flew everywhere. And we said, well, God damn it! We looked at the finite element analysis, and everything was fine. Like, how did this thing possibly break? There was a margin there of several percent. Like, how did this happen? I'm about to lose power here. How did this thing not even go an hour? We're almost done anyway. How does this? Does anyone have a plug on them? I don't know. Let's see. Is that actually supplier? Sorry, guys. This thing will go a couple hours before it turns out juice. I don't know what happened. Don't have it, anyone else have anything, like a normal, like rectangular one? Or a, what's this thing, a Lenovo? Right back, I don't want to lose something right back, sorry. Sir. Really sorry about this, guys.
All good.
Okay, here we go. You probably do, yeah. So the thing blows up. No one can figure out why. No one can figure out why. Oh, why it blew up. The thing blows up. No one can figure out why. This is right about when I started working at this company, and what had happened is that the place that was manufacturing this motor and putting the housing together, what had happened was that they were taking the aluminum, and rather than heating it up a tiny little bit and then dropping the stator in for the electric motor, what they were doing is they were sticking in a furnace, and it was staying there as long as 6 hours at 400 degrees Celsius. Okay, so we looked at the microstructure, the precipitates were visible, they're huge, and that's why the material failed, because the strength had dropped so dramatically because they overcooked this thing. So I've seen this a lot where manufacturing will not be aware of this precipitation coarsening problem and end up with a part that fails. Another time I've seen this happen is powder coating. So if you powder coat a part, like you know about powder coating, you have a metal part, and then you have like a steel part, for example. Then you charge the particles, little paint particles, tiny paint particles. You charge them up, and you know, put them in the same place. They go together and coat the part, right? And then you stick this thing in a furnace, and the paint melts together. It melds into a nice shiny surface. It's called powder coating. It's probably, I'm sure these desks are powder coated. Probably this thing's powder coated over here. It's here. Heater thing, heater housing here. So you guys see the problem there? Like if they cook these things too long to melt the paint, you can coarsen the material and it can fail. So it's something you need to be aware of. You know, watch out. If somebody's cooking your part, if it's made out of aluminum, it's a precipitation hardened material, go to the darn factory and look what they're doing and make sure that it's not cooking this thing. Because with this case with the motor I'm talking about, I never would have known about that unless I'd actually gone to the factory, talked to one of the line workers, and said, hey, what's going on? Describe to me exactly what you do. And they say, well, we start a shift out, we put the aluminum in this furnace. Yeah, and then when we get to them, well, how long is your shift? My shift is 8 hours. So how long do you think the parts in there? They probably don't stay in there more than 6 hours. What's the temperature on the furnace? 400 degrees Celsius. We got a problem here, guys. So always watch out for those kind of things. Let's see here. Okay, why don't we do, see, it's 9:55. You guys want to do one more slide and then we'll adjourn for the day? Okay. So we talked before about increasing the amount of energy it takes to move a dislocation through a lattice of metal in this case. And that you can strengthen a material by making it so it takes more energy to move this dislocation through the lattice. We talked about that. One way we talk about doing this is precipitation hardening. That's what we just talked about. And when precipitates are very small, you know, they can be like in the nanometer scale, really small. In fact, a lot of times they say that if you can see a precipitate in a microscope, it's too big. So these things are oftentimes really small. When they're really small, like down over here, these precipitates are really small. When a dislocation moves through the lattice and it gets to that precipitate, in order to keep moving through the lattice, when they're really small, what they have to do is they have to actually cut through the precipitate. That takes a lot of energy. That's very effective at strengthening materials. When these little precipitates keep growing bigger and bigger, eventually it gets to the point where it's thermodynamically favorable for the dislocations to actually wrap around the precipitate. Right, and this is actually what it looks like. This is a transmission electron microscope micrograph that shows dislocations wrapping around precipitates. This is real. And then when you get to this size, it takes less and less energy in order to get the dislocation to wrap around and move past. They call it looping, loop around the precipitate and keep going. And then the strength of the material goes down. So there's an optimum size where you're using this cutting mechanism as long as you can until the precipitate gets too big. It's an optimum size right here where the threshold between cutting and looping takes over. And this is where you want to, ultimately, this is where you want to artificially age the precipitate so that they're this size right here. And that, you probably say that's pretty damn abstract or just a graph. I don't know what that means. But it's different for different materials. But if you go back here, that point corresponds to the maximum artificial aging strength. Okay, so yeah.
Why do you want it to be at that critical size so that like you get some dislocations that wrap around and some dislocations that cut right through?
Well, there's some threshold where the amount of energy gets so high to move the dislocation that it takes less energy just to wrap around it. But the point is, you're just trying to get to that point where it's harder and harder and harder. It takes more and more energy to move it, just to that threshold where it'll start wrapping or looping around instead of cutting.
Gotcha. Okay.
So you're just heat treating to that point where you just it's cut through. It's that last little bit of energy to cut through versus looping around. That's where you meet the optimum strength of the material. Okay, so bigger picture, guys. As you're seeing now that if you want a lightweight material, you need to increase that strength to density ratio. There's mechanisms I've just showed you can use to strengthen the material. These are real things you can design into real materials. And this is that little component of creating the lightest, most efficient structure possible. The materials. How do you engineer the materials to the highest strength to density ratio? Next week we're gonna talk about a couple other mechanisms, right? So we're looking now pretty much. So we're looking at these different mechanisms for strengthening. In the middle of next lecture, we'll start to talk about how do you process the material in order to get these microstructures? How do you fill in that structure, or sorry, that processing structure link? That's going to be primarily what we talk about next time. Next time is tomorrow, 9 o'clock.
Thank you.
Okay, thanks, guys.
Strength.
Sorry, let me just stop the lecture here real quick, and then I will. Okay.